are at 4.2, and 4.2 is all about what the derivative tells us. Now, I'm going to emphasize this a lot. You have to demonstrate why these things work. You have to answer the question, how do you know on a regular basis to get points on the AP exam? You must demonstrate using words or symbols that you know what you're talking about. And I'm going to highlight some of those things as we go through here. So what we're going to be able to do here is we're going to be able to find where functions are increasing and decreasing, and we're going to identify and classify, meaning put them into a category, local extreme values. And we're going to use a calculus argument to do it. Much of what we do today, you should be able to say, well, that makes sense based on the function we see because of what I know about the function from higher algebra and pre-calc. What we're going to do is we're going to defend what we already know about these functions, but you have to make a calculus argument in order to get points for them on the exam. Okay? So let's take a look at the first question. How do you know if a function is increasing? Positive slope is a great phrase. Positive slope. Can we write that down? Is that fair? Positive slope. I think we can do better because this is an Algebra 1 argument, isn't it? This is an Algebra 1 argument. Let's make a calculus argument. How do we know if a function is increasing? F prime, which is the derivative, f prime of x is greater than 0. That's a calculus argument. That's worth points. The first one isn't, but this is a true statement. Positive slope is important to understand, but this is the calculus argument. A function is increasing if the derivative value is positive. That's huge. So if an AP exam question said in a basic sense, I don't know if they'd ask this, but when is the function positive? Or I'm sorry, when is the function increasing? You would say it's increasing on this interval because the derivative is positive. And you'd have to have a little bit of work to back that up. We'll go through that throughout the rest of the hour. Good? Okay. Algebra argument. How do you know if a function is decreasing? Negative slope. That's a great algebra argument. Negative slope. What's the calculus argument? F prime of x is less than 0. Okay. Good so far? That's a calculus argument. And you should have work to back it up. We're not dealing with a specific function yet, but one of these minutes we will. Okay. Good so far? Negative slope, the graph is falling. Positive slope, the graph is rising. Doesn't have to be linear, but in general, the trend has to be rising to be positive, to have a positive slope, falling if it has a negative slope. Good so far. These are not new, crazy, outrageous ideas yet, right? All we're going to do today is defend what we know, but the key here is defend it. You have to be able to answer the question, how do you know? So, next question, top of the second page of your notes. How do you know if a function has a local extreme value? What must be true about the derivative based on what we've already learned in section 4.1? What do you know? Continuous at a closed interval applies for the max-min existence theorem, but there are functions that have local maxes and mins that don't satisfy the extreme value theorem. Okay, curves or turning points is really important, right? So an extreme value will occur at a turning point that looks like that, or we've seen on rare occasions where we have extreme values right there. So what must be true about the derivative? F prime of x must be either 0 or undefined. Okay? Can we say equals undefined? You probably could. I don't know if they. I don't think they'd take off points. I think that'd be okay. That'd be okay. They, you kind of have to be careful with the use of the equal sign because the equal sign a lot of times implies a value is coming. It's not the end of the world. You'll probably be okay because you're saying the same thing. Okay. So here is where we get to, now we know if it's increasing if the derivative is positive. We know it's decreasing if the derivative is negative. Here's where we get to classifying critical points. All right. So using a calculus argument, we found a critical point, just like we did on the warm-up activity where we did number 1 and number 2. We identified the critical values. We identified the places where the derivative is 0 and where the derivative is undefined. Here's the first derivative test. Will you just read it really quick to yourself if you haven't done so already? Underline keywords in those definitions if you'd like. Does all of that make sense? Is there anything confusing at this point? If the graph is rising and then the graph is falling, what has to happen in between? F prime is 0 or F prime is undefined, and it is a what type of point? It's rising and then it's falling. There's only one way this could happen. If it changes sign from positive to negative, what has to be in here? A what type of point? A maximum has to be there, right? That makes sense, doesn't it? You have to be able to use the language to defend it. If F prime changes sign from negative to positive, what has to be in there? A minimum. Okay? If F prime does not change sign, not changing sign means it's positive, then positive, or negative, then negative, what is in there? Might be a jump, but it's probably not going to be a jump because we've already kind of determined continuity in a lot of ways. I know we didn't formally talk about continuity, okay, but something weird's happening. If the derivative is 0 or undefined and it's a continuous function, it has to be one of these. Yeah? You've seen those graphs before, like y equals x cubed? Okay. There's not a local extreme value there. It's got a positive slope to the left, it's got a positive slope to the right, and for a moment there, f prime is 0. Okay? So just a couple little pictures to tie into first derivative test. That's the big thing that we're doing today. But, I'll say it again. You must defend your answer using words or symbols from the first derivative test. That's what AP is looking for. Because I'm going to give you a cubic polynomial. I'm going to give you a cubic polynomial. You're going to have to show the work to tell me that it rises, then falls, then rises. But everybody knows that cubic polynomials typically rise, fall, rise, don't we? We know the behavior of a cubic? Rise, fall, rise. We're going to have to do some calculus in order to defend it. Okay? Questions at this point? At this point, you would say that you'd identify that point as a critical value that is neither a max or a min at this point. Now, going down the road, there will be another definition for this type of point, but we're not going there today. Okay, there's another word we use for a point like that, but we'll get there one thing at a time. Okay? All right, let's find an example. Example, find where the function is increasing and where the function is decreasing. Find the local extrema and justify your response. Okay? The big thing here is you have to defend your answer. Because what type of function is this? It's a cubic polynomial. We all have a pretty good idea of what cubic polynomials look like, right? Okay? We're going to be able to find the maximum value. We're going to be able to find the minimum value. And we need to identify intervals of increasing and decreasing using a calculus argument. Because this is a calculus class. But we're going to use what we already know. All right? So we know that it's cubic, so it probably looks like that. It's fair to draw that on your page right now. Okay? Unfortunately, on the AP exam, a lot of the functions are going to be a little more unfamiliar than this. But it probably looks like that. We all okay with that? Okay, so let's defend it. In order to find where a function is increasing and where a function is decreasing, it's really important, first of all, to find out where those could change, which are the critical points. A function is not going to change from increasing to decreasing without a critical point in the middle, just so you know. All right? Asymptotes throw things into a little bit of a weird mix, but we're not going to go there just yet. Okay? So, and actually asymptotes would be a critical value. So that would fall into that category. But for this example, it's really important to note that a function will not change direction without having a critical value in between them. Okay? So we need to find the critical values. How do we find the critical values? Set f prime equal to 0. This is worth points. F prime of x is equal to 6x squared plus 6x minus 72. And I want to go ahead and set that equal to 0. Okay. We already know that this is polynomial, so there's not going to be sharp corners or asymptotes. So I'm going to ignore the possibility of singular points at this point, and it's fair to do so. We know it's polynomial, we know it's continuous, we know there's no sharp corners, we know there's no asymptotes. You good on that? Okay. If the function is a little less familiar, if the function's less familiar, we need to consider the possibility of singular values as well. But let's go ahead and set that equal to 0. What do we got to do? Factor out of 6. Leaves us with x squared plus 1x. 72 divided by 6 is 12. Factor again. X plus 4x minus 3 equals 0. So we now know that there are critical values at x equals negative 4 and x equals 3. Okay? Good so far? You all know what happens now, though, right? Which one of those two x values is going to create a maximum? Go back to this drawing up here in the corner. Go back up to this drawing in the corner. Is the max going to be first or second? The max is going to be first, so where's the max going to occur? X equals negative 4, and the min's going to occur at 3. We know that, right? That's not worth points, though. Can I show you what's worth points? Figuring it out. You have to make the statement from first derivative test. Here's how I encourage you to show your work. This is what I'm going to look at. I'm going to take a number line, and this is how a lot of calculus teachers demonstrate first derivative test. You're going to break up your domain into 3 sections. And I break them up into 3 sections based on critical values. Okay? Because there are no other places on the function where it can turn. Okay? So to the left of negative 4, all the derivative values are going to have the same sign. They're all going to be positive or they're all going to be negative. In this interval, all the derivative values are going to have the same sign. It can't turn in the middle of there because there's no critical value. And all of the derivative values in that region are going to have the same sign. You're familiar with interval testing from pre-calc, right? Okay, so let's do this. What I want to check now, it's called the first derivative test, so I'm going to test the first derivatives. Make sense? Now, here's the beauty of it. I can pick any value in this interval that I want. I want to find, let's say, f prime of negative 5. I don't want to be crazy about my values because I want to have something that I can reasonably accomplish, but, and depending on the function, you're going to choose your values pretty purposefully. Okay? If it's a polynomial, factored form's a good way to go. If I put in negative 5, the product I would get here would be 6 times negative 1 times negative 8. You with me on that? I'm putting in a negative 5 there, and I'm putting in a negative 5 there, because that's the derivative, right? So what is the derivative? What is the value of the derivative at x equals negative 5? Positive or negative? Positive 48, which means the graph is Positive isn't the right word here. The graph, now I'm going back to the graph. F is increasing. So I'm going to go ahead and I'm going to add a little bit of a picture for myself. The graph is increasing there, okay? Which we already knew, but you have to show this work to defend it. I realize it's painful, but you have to be able to defend your work, okay? Let's find something in between -4 and 3. 0 is a good one. F prime of 0 would be 6 times 4 times -3, which gives us a value of frozen smartboard. Awesome. Equals -12. That's not -12. That's something a lot bigger than -12. What's really important is that it is, what is it, -72. -72, right? Okay. What's really important is that, not that it's 72, but that it's negative. So the graph in there is falling. Decreasing is actually a better word. Okay. F prime then of, let's pick 4 because 4 is in our third interval. F prime of 4 would give us 6 times 8 times 1, which is 48, which is more importantly positive, so the graph is rising. Okay. Let's answer our question now. We've done most of the work. Let's answer our question and defend it. So it asks us to find where the function is increasing. It is increasing on what intervals? -infinity to -4. Do I include -4 or not? No, because is it increasing at -4? No, it's horizontal. It's got a horizontal tangent. It is also increasing on the interval from 3 to infinity. And when is it decreasing? Decreasing on -4 to 3. Okay. Why is it increasing on these on these two intervals? Why is it increasing here? F prime is greater than 0. Why is it decreasing here? F prime is less than 0. Guys, that's worth points. You want a 9 out of 9 out of an FRQ, you're going to write that stuff. Okay? So we did increasing, we did decreasing. Find the local extrema, what do you say, extrema or extrema, and justify your response. Okay? What type of point is the point that occurs at x equals -4? What is it? It is a 2 words. Okay, give me more. It's more than a stationary point. We can be more specific at this point. It is a local maximum. Why? It is a local max because phi. F prime, here's the appropriate response. F prime changes from positive to negative. That's how you defend a max. Okay. What about x equals 3? It's a local, what? It's a local minimum. Why? F prime changes from negative to positive. If you want to know what's worth points, guys, it's the words over here. Okay? It's the words over here with this work to defend it. Okay? No, the line, good question. The line thing is not enough. It used to be. The number line test used to be enough on the AP exam. They stopped allowing that to be enough. I don't know why. Now you're allowed to use the number line thing, and I think you should. But the defense with the words over on the right is worth points. If you don't have the number line, you still get points. But if you don't have these words and you do have the number line, you don't get the points. I get that that's a tough idea to grasp, but that's kind of where we're at. That's what they tell me that is important. Well, love them or hate them, they are what they are, and they write the exam and they set the rules. So if you don't follow the rules, you don't do well on their test. But you'll be okay making your own test. I think it's a great idea. Let's look at example 2 really quick. Find the local extreme values. Find where the function is increasing and where the function is decreasing. This one is going to be a little faster, and let's talk about why. What do we do first? Derivatize. That's not a verb, but I know what you mean. Find the derivative, which is e to the negative 0.5x, give me more, times negative 0.5, right? That's our derivative. Negative 0.5 times e to the negative 0.5x. Okay? Let's set that derivative equal to 0. And we get a couple of people shaking their head, a couple of people saying undefined. It never does. Good. Good. I could divide by negative 0.5, and I could get e to the negative 0.5x equals 0. You need to be able to state that e to the negative 0.5x, x is up here, is never 0. Which implies what? There are no critical points. Which means, here's the big conclusion. If there are no critical points, the graph will not change direction. You thought we had a singular one? Are there any places where, good question, are there any places where that function is undefined? No. There's nowhere that that's undefined. Why? What do we know about e to the x? It's continuous. It's differentiable on its entire domain. Okay? But we could, guys, I went through this too quickly, and I did it on purpose. I want you to go back. I want you to go back to what you know about this function. What type of function is this? It's exponential. Is it growth or decay? It's exponential decay, which means it goes through this point, 0, 1, and the graph looks like this. Does the graph ever change direction? No, the graph is decreasing on its entire domain, which we knew. Okay, but here's how you defend it as a calculus argument. There's no critical points, so we need to test an f prime value. What's your favorite x value to put into the e function? 0 is a great one. Let's test f prime of 0. F prime of 0 is negative 0.5 times e to the 0 power, which is negative 0.5, which means the graph is, no, the graph is decreasing for all x because f prime is less than 0 for all x. This statement with this work is worth your marks. That's where you get your points on the exam. Does that make sense, or do we need to clarify something on that example? This is hard. This is a little bit hard, especially when we get some unfamiliar graphs. But if there aren't any critical points, the graph can't turn. Does that make sense? And if the graph can't turn, the graph is either always increasing or always decreasing. We need to determine which one it is. So we can check any value we want, and we know that the graph is decreasing because the derivative is negative. And if it can't turn, the graph has to be decreasing for all x values. Okay? But it's really important. I jumped into the calculus really fast right away, didn't I? And I didn't, like I did on the first one, I didn't draw this immediately, but I think that's important because if you have that in your frame, your work down here makes a little more sense, doesn't it? Okay. Here's where we're at. Day 1 homework is here. It's on Schoology as well. I want to warn you a little bit. I don't want you to spend a ton of time on the self-check review problems. These are those kind of concept problems at the beginning. And also, we haven't gotten through all of the 4.2 material yet, so really you can only do like 1 through 4 at this point. And 5 through 10 apply to what we're going to do tomorrow. So when you do the self-check problems, go 1 through 4. This is where a lot of the skill-based stuff comes in, so spend more of your time there. Questions so far? I don't have a calendar for you yet. That's a good question, and we are working on that, so that'll be coming soon.